Okay, so let's get started. Sorry I'm a little bit late getting started here. I was sitting working away at my desk and forgot to go to class. I used to do that in grad school too, but
burnout.
I looked at my wife, oh, gotta go. So here we are. Today is review for the test, which is Wednesday. What chapters does this test cover?
All of that.
Right, mostly just 9 and 10. There was one concept out of 8, which I did not remember to put on this review, but that's relative risk. So you can remember that. You need to know that too. But also MA343 review. So there'll be a few questions on there that just make sure you understand the concepts from MA343. Now Brent was in asking me a little bit earlier, how do I remember all these different tests that you can do in your calculator, right? You got one SAMP-T test and one prop Z-int and two. I'm not going to make you know all those things, right? It'll be more like these were, which are just concepts. You want to compute hypothesis tests and confidence intervals from MA343, okay? You will, MA343, you learned how to use your calculator to do a linear regression. You may have to do that. And you will need to do a chi-square test. All right? But other than that, all the other stuff, means and proportions, you won't have to do. So the plan today is to go through this review and answer the ones that you didn't know how to answer on your own. Ones that everybody got, no problem. We won't waste class time on it. So just answer or ask questions, which ones you want to see. Yep. Number 4. Okay. Let me scroll that up. And number 4 says, let me see if I can make this even bigger without distorting it too much. There we go. It's a goodness of fit test. This is I took straight out of the book. It's problem number 952. What's all that? I don't know how to get rid of that. I guess it's all right. It says you generate 500 random numbers, and they're supposed to come from a uniform distribution. So your calculator is supposed to generate random numbers, and if it's uniform, what does that term mean?
It means the same probability of getting each number.
That each number should be equally likely. They're categorized into 5 groups. Numbers that are less than or equal to 0.2, greater than 0.2, but less than or equal to 0.4, and so on. So you're taking the possible values 0 to 1 and chopping it into 5 equal intervals, right? So the counts in the 5 groups are, so let's do it this way. There we go. If I have
Tax mark.
escape, and it's in red, it looks like, but I'll just call it. What in the world? I'm gonna go back to that. Yeah. Group, right? So the first one is less than or equal to 0.2, and then
Greater than 0.2.
yeah, 0.2 to 0.4, and so on, and keeping track of where the greater than and the less than is and all that stuff, right? So then count. So 3, 4, 5. So I won't take the time, but you can figure out what those headers are, right? So the counts in each of those are 114, 92, 108, 101, and 85. For a total of, if you sum those up, you get what?
500.
You should get 500. Because it says they generated 500 random numbers, and here's how they split out. All right? Now, it says, do a goodness of fit test to see do the observed counts fit what you would expect if these were truly uniformly distributed. So what's the next step?
So we have to make it expected chart.
Make an expected row. So I'll abbreviate that EXP. And what would you expect? 100 each, right? Because they're uniformly distributed. There's 500 total, 5 slots. That'd be 100 in each of those. Right? And now they made this one nice by having a nice multiple of 100 for your total. But suppose they say you generate 684 random numbers. Then you just take, 1/5 of 684 should go in each of those slots. Right? So the goodness of fit test, then, how do you form the test statistic? Okay. So the chi-square test statistic is the sum of observed minus expected squared over, and the over should just be, I need to erase that little, my line got a little too long. There you go. Right? So the summation is all of that. So you just take observed minus expected, square that, divide by expected. Since all the expecteds are the same, 100, you could actually factor that thing out and do it. But what do you get when you do that? You got what? 5.5? Okay. I'm working on the solutions document to this, which I will post after class, but I don't have it where I can pull it up here yet. But anybody get something different than that? You can actually do, some of these calculators will do the chi-square goodness of fit test. You put the observed counts in a list, and then I think you put the expected counts in the next list, and it'll do it. All right. So you could put these in L1, not the totals, but and then the expected into L2. All right. So 5.5, and that's been rounded off. But now, how do I get a p-value for that test? Okay. So the p-value is the chi-square CDF function on your calculator from left to right, or lower to upper, and it's 5.5 for the left edge of the shaded region up to infinity. So in your calculator, you can enter that as a bunch of 9s. And then comma, what? Degrees of freedom. So we need to know degrees of freedom. 4 degrees, one less than the number of cells that got summed up. Right? So degrees of freedom is 4. So put a 4 there in your calculator, hit enter, and what do you get? 0.2397. Okay? So what's the conclusion of that test? That's a big p-value, right? So you're going to fail to reject the null. Oh, you mean there's a null and an alternative? Yeah, any test has a null and alternative, and you need to know what those things are, even if it's not stated. What's the null hypothesis?
Null hypothesis that it does fit.
That it does fit. The fit is good. She was right. I just paused to see if I could get her to change her mind. Right? So the null hypothesis, and remember, it's kind of backwards with the goodness of fit test. The null is what you hope to prove in this case. Usually it's the other way around. So we're failing to reject that the fit is good. So the way you would word your conclusion is, we do not have sufficient evidence to say that the data, or that the random number generator is not uniform. Right? So we fail to reject that it is uniform. So we're saying, yeah, as far as we can tell, it's good enough. Okay? Now, if you're really doing this with a computer, 500 is probably not enough. I'd probably do 5 million. do 5 million of them, and get smaller intervals and see what you come up with. And if you do enough, eventually you'll probably get so much power to detect small differences that you could say, well, it isn't exactly uniform, but it's reasonably close. So. Okay, next question. Uh-oh. How do I make the words go with it?
You don't. It's printing on the screen. You have to just clear it.
So I have to clear it. Okay. I was wanting to save it, so I had a key to post for you. Ooh, that ain't good. That cleared the whole PDF file.
Do the undo. There's right next to it. Edit.
That one?
And then just hit the spray bottle.
I'm glad you know what you're doing. Spray bottle, clear annotations. Got it. Thank you. Okay, so now I want to scroll up. What about the M&M's one?
Yes.
It's another goodness of fit test, right? And so make the same table. I'm going to use black ink this time. Make the same table observed, only now I got categorical variable. I don't have to do this thing of chopping it up into a certain number. It's already been chopped up, and it's brown, yellow, red, orange, blue, and green. So brown, BR, yellow, red, orange, blue, and green. Right? And then expected looks like that. Okay? So now it says you open up a 14-ounce bag and find 61 brown, 59 yellow, blah, blah, blah. So 61 brown, 59 yellow, 49 red, 77 orange, 141 blue, and 88 green. So now how do I get my expected counts?
There's the probabilities
Exactly.
of the total.
Times that by.
Now, first of all, we need the total, don't we? How many M&Ms were in this bag?
475.
475? Okay. Now, we don't evenly distribute like we did with the previous problem. It's not 1/6 of 475. You do it according to the percentages given. You expect that 13% of the 475 would be brown. So what is 0.13 times 475? And keep a couple of decimal places. 61.75. That looks pretty good. We expected 61.75. We got 61. Next one. 14% yellow.
66.5.
66.5. And is it 0.5 even, or is it?
0.5 even.
Okay. So I'll put a 0 to indicate we went to 2 decimal places. And then red, 13. That one we got already. 61.75. 77 orange, and we expected 20% orange. 20% of 475. 95. Even? I didn't make this up. I took this out of the book. And then blue. We expect 24% blue. So 24% of 475. How much? 114. And then finally green. We expect 16% green. 76 even? Okay. Now, I don't think, well, let's not take the time to go ahead and finish this out. But from here, do you know what to do? Exactly what we did on the last one. You just take, you got 6 things to sum up now, but observed minus expected, quantity squared, divided by expected, sum them all up. You get a chi-square test statistic. How many degrees of freedom? 5. 5 degrees of freedom. You can't do the rows minus 1 column because there's only 1 row. But, yeah.
Are you going to want to see your statement steps, or can I use the goodness of fit?
Yeah, can we use the goodness of fit?
You can use the goodness of fit test on your calculator if you have it. But I will probably ask you something like, what's the contribution to that test statistic from the green M&Ms? Or something like that. So you have to do one of the pieces by hand at least. Right? So who's got it finished out? What's the p-value? Anybody got it all the way done? I'm skipping the computation of the chi-square test statistic and all that.
$0.0312.
0.0312. Okay? Anybody disagree with that? Okay. What's the conclusion? You would reject the null and say, hey, what the company told us the percentages are doesn't look like that held for the bag that we opened. Yeah.
You want us to just assume 95% confidence?
Right. If it doesn't say 95% confidence goes along with alpha equal 0.05. So if they don't say what significance level to use, then assume 0.05. Yeah. Okay. So you will reject the null hypothesis. And it's funny, I don't do it all the time, but sometimes I'll use M&Ms as an example when we do proportions or whatever, and we open bags of M&Ms and just count what percent are blue. And it's rarely close to the 24% that is on the company's website. So they've changed the colors since this got updated, and they quit updating their website because their website still says 24% blue. But it's different than that now. You can see here that it's way more blue than you would have expected. Right? So they're putting lots of blues in there. So reject the fit. That's a real cryptic way to say the conclusion. You reject that this fits the data.
Hey, my p-value is wrong.
Your p-value is wrong?
Oh yeah, I forgot to put one on that.
0.009.
Yeah.
So it's even worse than this.
Yeah.
Okay. 0.009. Give me one more place. 91. Okay.
1.96.
So now you're really rejecting the null. Luckily, you still got the same conclusion, but you still miss all the points. Okay. Next question. Undo.
To the right of the toolbar.
There you go. Undo. Now I gotta go here. Then.
That is what you got to take.
Oh.
There you go. Now I gotta explode that up. That's where I get into trouble. But it wants to rotate on me.
Yeah, I think if you put your fingers farther apart, less likely to rotate.
Oh, that's kind of like more spread in your X and you get less tilt in your...
I see you appreciate that.
Okay. Any questions on this problem? What kind of a test do you use for this? I won't read the whole thing to you, but it says...
Chi-square.
Oh, it asked a lot of stuff before. The questions down below test to see if there's a relationship between what kind of intervention they do and whether or not they respond. And it'll be a chi-square test for association. Good. Right? So find the row and column totals, put them in the table, in the margins of the table.
435, 648.
That's up here? Okay, let me get that. So 435, 648,
1083.
1083.
And that's 391.
And that's over here? So then you're just totaling the columns.
354, 338.
And 338. 338. Okay? And those three numbers should add to the same thing that these two numbers add to.
And to get the percentages, you do it based off the total.
It depends on what they ask for. So let's see. Compute the marginal distribution of yeses and display those percents. That's these percents. So what are they? When it says marginal distribution of yeses and nos, that means in the margin of the table. Right? So you know that's row totals. So the row totals divided by the grand total. So 435 divided by 1083 is what? 0.401.
40.17.
So this has a percent sign after it. So 40.7 you said? 17. Yeah. So 40.17, and I'm writing too big for my percent sign, so there's 40.17%. Next one?
59.83%.
59.83%. Right? So roughly 40% and 60%. 40% said yes, 60% said no.
Then those would be against the total.
Right, these are against the grand total.
Right, those are against that total. And
Right.
these are against that total over there.
Ah. Oh, this darn thing. I wish I had a scroll bar over here that would take it all with me. I read this in as a PDF file because a Word document wasn't an option, so I don't know how to do it. But let's just clear all that stuff. So you'll have to go from your notes to get the numbers in the table. It now says display conditional percents from part B. All right, we haven't done B, have we? For each type of intervention, find the conditional distributions of yeses and nos. Huh? Conditional distribution of yeses and nos for each type of intervention. If it's conditional, it's either a row percent or a column percent. Which is this? Column percent. Because the interventions form the columns. Right? So this says my battery is low. So unfortunately, we may not finish the class before that goes dead. But so let me scroll down just a little bit. The conditional distributions, and you're supposed to put them in here. So what is the conditional distribution of yeses? I've erased the column totals, but you would divide the 171 by whatever that column total was. What do you get?
0.3931.
I get 43.73%.
43?
Yeah, 0.73%.
0.73%. That's moving the decimal two places to make it a percent. I wouldn't get picky about that. What's the next one?
41.24%.
41.24 and 34.91. Okay? Everybody getting those? And then what about the no's?
You just take 1 minus.
There'll be subtractions. Take 100% minus 43.73, you get this one. Or 1 minus the proportion. Okay, so I won't bother to write those out, but that's how you get them. Display conditional percents from B in a side-by-side bar graph. Okay? Side-by-side bar graph. You're going to have yeses and nos side by side for each intervention. And I already forgot what the interventions were.
Letter,
phone,
So letter, phone, and none. So an N, right? And then you have a bar for the yeses. So it was 43, 41, and 34. So there's 43, there's 41, and there's 34. Right? And then the no's will be 1 minus that, so the no's will be 60-some. And this one will be a little bit taller, but not much. And then this one will be a lot taller. Man, that's pretty. Okay? Now we get to the testing part. Give the null and alternative hypothesis for testing whether intervention made any difference. So that's the chi-square test of association. What's the null?
That there is no association
Okay, there is no association
between response and what type of intervention.
between response and intervention. And then the alternative, there is association. So instead of the word no, you put an, and copy the sentence. Right? Assuming no association between intervention and response, how many people who received letters are expected to respond? Show the calculation. So how do you do expected counts?
Row divided by column.
Okay, good. So expected count is row total times column total divided by grand total. And what are those numbers before we do the calculation?
What is the bottom side?
It says GR for grand, and then some kind of weird looking T, TOT for total. So grand total. This thing's hard to write with.
The grand total was 1083.
Okay, so the bottom is 1083.
and then it's 435 times 391 for that.
435
Yep.
times what?
391
391.
per yes and letter.
Okay, and then as a multiplying it all out, what do you get?
157.0498.
049. So I'll call
I guess it would round to 0.5.
Yeah, that's probably close enough.
But if you wanted to.
Okay, so 157.05. Okay, so that's the expected count you would have for that particular cell of the table. And then give the contribution to the test statistic for that cell. So you would take the observed count, which is what? I can't see it.
71.
What?
171.
171. Okay. 171 minus 157.05 squared divided by the expected, which is 157.05. Okay? That's the contribution of that one cell.
This is 1.23 or
1.24. Okay? Then you do that for all all 6 cells, sum them up, and you'd have your chi-square test statistic, which would be, start to say on the next page, but it's not. But is everybody done with this? I'll clear this and scroll up. Can't remember how to do this. There we go. find the value of the test statistic, and give the p-value. So we've done that already. The main thing now is we got to know the degrees of freedom. So what are the degrees of freedom when you have a contingency table? This test of association. Yeah, now it's row minus 1 times column minus 1. Rows minus 1 is 1, because there's 2 rows. Columns, there's 3 columns, so 2. So 2 times 1 is 2 degrees of freedom. So what did you get for your test statistic? When you sum up all 6 cells, or you enter it into a matrix in your calculator and you do the chi-square test, what do you get for your test statistic? $6.1255. I put 6.1. So 6 point, say it again.
1255.
1255. Okay? That doesn't look very big to me. Although remember that it's kind of hard to get a feel for the size of the chi-square test statistic, whether it's big or small or whatever. So we really need the p-value.
0.04676.
Point what?
0.4676.
Oh, 0.476. That's smaller than I would have thought for that.
4676.
Yeah, 4676.
But it does have a leading 0? Okay. So what's the conclusion? Reject the null. Remember what our null was? There's no association, so we're going to reject that. Say there is an association between response and type of intervention.
Because it's below the alpha.
Because it's below alpha, which if it's not stated, and I guess it was stated here, alpha is 0.05. Since that is less than 0.05, then you're going to reject the null. Okay? We are quick running out of time already. So let's look through the next few are kind of just look at plots and things to try to interpret. Number 7 says, okay, your fingers have to be inside of it, I guess. Number 7, if we produce 95% confidence interval for the slope, approximately 95% of all possible samples would provide slopes that fall within that interval. Is that correct? Not quite. It's not quite. What does it mean? Or what is the correct interpretation?
There's a 95%. We have 95% confidence that the mean of the population lies somewhere.
Okay, don't say the mean of the population, because we're talking about slopes here.
Yeah, okay. The true slope.
The true slope falls in that interval,
There you go.
which the definition of confidence is that if you took a huge number of different samples, 95 and produced a confidence interval from each of those samples, 95% of the confidence intervals would contain the true slope, which is not quite what this says. So it's technicality. This sounds pretty good, but it's not technically quite correct.
So it would be the true slope would be within the interval.
Right. 95% confident the true slope is in the interval. And that's fine for an answer. 8 says the resulting line must go through what point? The centroid. X bar, Y bar. Okay, what's wrong with this plot? It's curved. One of the assumptions is you need a linear relationship. What's wrong with this plot?
Constant variance is violated.
Constant variance is violated, right? Yeah, exactly. It fans out. So you see that shape, right? So it's getting more spread out as x gets bigger. Now draw a residual plot next to it. So a residual plot has a line in the middle at 0. What would that residual plot look like?
It's even just returns on its side, right?
Yeah, basically you take this and put it there. So you'd get points that are spreading out more and more as you go. Now I wasn't careful to try to make them match up with those, but technically they would.
Do you want to dock us for that?
I probably wouldn't have you sketch one because people's hand sketching are just horrible. So I would say, here's a plot of something, what do you see? Right? Okay, so let's get to the fill in the there. I'll let you do these, okay? Everybody okay on those?
Make it bigger.
Is it just what is R?
Yeah, what is R?
Make it a little bit smaller.
Look at the pictures and figure out what R is, right? So,
Okay, so just math.
some are strong, some are weak.
R equals 0. It's that last one. And then what about that one next to it?
I'm too OCD for this. This one?
Graph E looks like there's no correlation here.
Right, here it looks like a shotgun blast, so this would be R equals 0.
And then the next one is R equals 0 too, right?
This one's R equals 0 because
There's no correlation.
there is a strong relationship, it's just not a linear relationship, and there's no prevailing up or down to it. So you get R equals 0. Right?
So it's okay that they're both 0.
Yeah, they're both 0. Okay. So number 12 says, is this statement true or false? In a simple linear regression, if we produce 95% confidence intervals for the mean predicted value of y for a wide range of x's, called confidence bands, and graph them on a scatter plot, approximately 95% of the data points would fall within the bands. Is that the correct interpretation of a confidence interval? Confidence bands?
Yeah.
It sounds good.
Sounds real good, but it's wrong.
Okay. Why?
That what is being described there are prediction intervals. 95% of points would fall between the prediction intervals, but in between the confidence bands, which are much narrower, would be we are 95% confident that the mean the mean value for, can I start that over? 95% confident that the mean value of y for that particular value of x will fall in between those confidence bands. The mean, not individual points. Individual points fall within the prediction interval. And remember, they're a lot wider than the confidence bands. Okay, 13 says 95% confidence bands are drawn around the line. Explain why the bands are narrower near the middle and wider near the end. So,
Look the undo.
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 There you go. Now, what do I got to do?
What do you use your marking?
That's what I wanted. I want to get it up there.
It's good enough.
That's the
Okay.
easier when you go wide.
It is. So here's a scatter plot, and you've got some data points going up like so, and you got a line going through there. The confidence bands will look like this. And I gave you formulas for the standard error that would be used for those. It says they're wider near the ends of the line and narrower in the middle. Why is that?
The variability on the ends is bigger.
Okay, why do you have more variability on the ends?
Because it's further away from the main two. You
Okay,
end up with a bigger thing that makes the square root or
the
something.
further away from the centroid you're trying to predict, the more error there is because you have to account for error in your slope estimate. Because a small error in the slope would tilt that line a lot out to the ends, but not tilt it it wouldn't make much difference in near it. So the standard error, remember the formula for the standard error of confidence bands?
SE times the square root of 1 over n.
S sub E, so that's the standard error of the residuals, or like Excel labels that standard error of the estimate, but then square root of
1 over n.
1 over n plus
X star minus X bar squared.
X star minus X bar squared over,
N minus 1 times SX squared.
okay, n minus 1 times Sx squared. That's not a very good X, but, right? So this piece is measuring how far away from the centroid you're trying to estimate. And if your X that you're trying to estimate is a long ways from X bar, this term adds a lot, so they get wider. But if you're estimating right at the mean, this term's 0, right? So it's minimized at X bar, so it's minimized in the middle and gets bigger as you move either direction away from that. That's why those bands get wider. Okay, number 14. I'm going to run out of time. Number 14 uses the formulas slope B1 is equal to R times SY over SX. Remember that formula? So they gave me R, that's correlation. They gave me summary statistics, so the standard deviation of Y is 4, standard deviation of X is 15.5. So you plug that in, you get your slope. Then once you have your slope, how do you get your intercept?
Plug in.
Yeah. Oh, it's just
Y bar minus B1 X bar. Right? So you've got Y bar and X bar as the means of X and Y. You now have computed your slope up here, so you've got everything you need. Just plug it in. You get, and then write out the equation write out the regression equation. It's just B0 plus B1 times X. Okay, now the fun one. I don't have time to finish all of this, but let's start by making it big, I guess. And then scroll it up. What's your strategy for figuring out how to fill in all these gray boxes?
start with the SS
Algebra.
Okay, SSE you can fill in by how?
It's 23 minus 10.
Subtraction.
These top two must add to the sum of squares total, right? So sum of squares for regression plus sum of squares for error must add. So you can get that one by subtraction. What about degrees of freedom?
N minus 1 for the total.
Total is n minus 1,
Residual is 1 since that's the number of variables.
and 1 because we're doing one x variable in the model.
And then it's
N minus 2 for the residual.
And it's n minus 2. And these two, just like sums of squares, the two top ones must add to the bottom one. So that leaves n minus 2 for that. Then how do you get mean squares?
It's the SS divided by the
Take the sum of squares, SS, divide by degrees of freedom, and you got mean square. Right?
R squared.
And then, yeah, r squared. Now, how do you get r squared?
You square R.
How do you get r?
Clear an equation.
There, you can't get r from this, but you can get r squared, and then you'll get r by taking the square root of
Root
it.
of it.
So how do you get r? R squared. R squared equal, it's the percent of the variability in the y variable that can be explained by the x variable. That's the interpretation of r squared, right?
And that's
So this sum of squares total is the total variation in the y. 23.98. What percent of that is explained by the model? Oh, that's sum of squares for regression. So you take sum of squares for regression, divide by sum of squares total, that gives you R squared. So this is sum of squares for, I use M for model instead of R for regression because both of these words start with R and people get confused. So sum of squares M over sum of squares total. So that tells you how to fill in that one. Take the square root of it, you get, Excel calls it multiple R, just to be generic for when you do multiple regression, but it's just correlation. But you have to be careful that you need to be careful to understand whether it's a positive or negative relationship. And you get that by looking at the scatter plot or by looking at your slope. Okay, so now how am I going to get the slope? Oh, I haven't finished up here. We got mean squares. How do you get the F statistic?
MS divided by, or MS.
Mean square for the model divided by mean square error. Right? So this is mean square model over mean square error. And it's an F statistic with 1 degree of freedom over n minus 2 degrees of freedom. Then you got an FCDF function on your calculator to compute. And I gave it to you here, but you could get that same number once you know this F statistic. Okay? Now, how do you get the slope? Hint, we just did it a minute ago. Once we knew the correlation, and we know the mean and the standard deviation of x and y, it's r times sy over sx, right? So this, you can use r over, so r times sy over sx. That's the same formula. I'll use the capital R this time because that's what's written up there. But and then standard error. How do you get the standard error of the slope?
Root MSC divided by n minus 1 times sx.
Yeah, let me just get a complete blank thing here. Standard error of B1 is SE, and what's that notation for?
Standard error.
Standard error of the residuals. So that's root mean squared error, right? So SE is square root of the mean squared error. And then on the bottom?
N minus 1 square root of n minus 1, sorry, times sx.
Times sx. Right? So the variance of B1 is SE squared over n minus 1 times sx squared. Then you square root the whole thing, and these two, and you get a square root on the n minus 1. Right? So that fills in your standard error. Now, how do you get the t-stat, t-test statistic, once you know the slope and its standard error? Anybody remember that? You simply divide. So this is B1 over SE B1. And then p-values from TCDF function on your calculator, but it's going to be exactly the same p-value as up here in the F statistic when there's only one x variable. All right? But you do TCDF from the test statistic to infinity, comma, error degrees of freedom. And then lower and upper bounds on a confidence interval.
It's just your observed or your predicted plus or minus.
This is I'm doing the slope line, but the same thing will be true on the intercept line. But confidence interval for the slope, it's the estimate of slope plus or minus
Your critical value
t critical value times, not times margin of error, times standard error that you just computed here. And that'll give you confidence interval. Okay, I'm way past out of time, but I can keep going if you want to stay and listen. If you need to get going, get going.
What was that being online though?
What's that?
Drop it in.
I will post the key to this this afternoon sometime.
And they'll have all this,
What?
it'll have all this on it?
It'll have all the right answers on it.
Okay, because I didn't get that formula you wrote on the other page. Yeah, could you revert back to the previous page you were on?
That's easy.
What was the B1 over SEB1?
Are you talking about this formula?
No, it was B1 divided by SEB1 something.
Oh, that's down here. B1 over SEB1. That's the test statistic
It
for.
was SE divided by the square root of n minus 1. Missed that one.
Where did I write that one?
You clicked new page, so.
Oh, yeah, that's over here. There.
There we go.
Right? So this is how to get the standard error of slope. These are all in the book, by the way. Right? And then the thing I ran out of time before we got to doing it was, now my battery's critically low, is confidence bands. So 95% confidence interval for mu hat, the mean predicted value. Remember that is SE times the square root of 1 over n,
Wait, isn't that plus 1? Oh, no, never mind.
and then x star. We did this once, right?
Yeah, we did that.
And then n minus 1 times sx squared. Now, if it's 95% prediction interval,
Yeah, the 1.
so pi instead of ci, for y hat, instead of mu hat, y hat, then it's exactly the same, but inside the square root is 1 plus all of the rest. So you add this 1 in there.
We're going to have to know all of these formulas. No,
You're going to have to write them on your cheat sheet.
Oh, we get a cheat sheet still.
Yes.
Still a thing.
You get a cheat sheet.
You know what I like about statisticians? They don't care for you to remember the 37 million formulas. They just care that you know how to use them. Yes.
And you know what? That's okay, because I can just Google it anyways. If you
I
don't
know, right?
I'll just look it up.
The best piece of advice I got in graduate school from my major professor was, you don't have to remember all this stuff. You just have to remember what book it's in.
That's my philosophy there, too. Hence why you have how many books that are statistics books?
Good luck on the tests.